What happens to a satellite when every signal goes silent, yet it keeps orbiting above us? Tonight on the Galaxy Scientist, we drift toward the forgotten bodies circling Earth in complete, quiet ghost satellites that slipped out of contact decades ago. They still move with us, tracing invisible paths, holding clues to old missions, lost intentions, and the strange calm of machines that never truly died. There's something soothing about their quiet persistence, drifting through the dark like fading memories. If this gentle curiosity feels right to you, a soft like and quiet subscribe. Help others find their way here. Settle in now, and let's follow these silent companions, unhurried and warm. Out there in the quiet places above our world, where sunlight fades into deep blue and then into black, traces of our earliest curiosity still drift. Most people remember the great names, the International Space Station, the bright plans for Mars, but long before these modern voices, there were gentler footsteps, old machines from the first age of exploration, voyages from the past, still wandering. Some circle our planet in slow, forgotten loops. Others tumble farther out, silent in the cold beyond the planets. They are like tiny echoes, carrying the memory of when humanity first learned to lift its gaze and reach. They may be nothing more than metal shells now, but each one is a time capsule, a small reminder of how brave and how uncertain those first steps were. Their stories stretch across decades, where they traveled, what they whispered back to us, and why their presence still matters, even as they drift unlit in the darkness. The beginning of this legacy lies with an empire that no longer exists. Before the great achievements that captured the world's attention, the early Soviet programs sent quiet machines into the sky. No crews, no return plans, only small satellites sent upward with hope and tension, carrying the dreams of a nation into the unknown. Many of these early travelers launched in the late 1950s and the early 1960s, and many of them still move overhead, rusting ghosts slipping through the silence. Everything began with a sphere the size of a beach ball. On the 4th of October in the year 1957, the first artificial satellite rose above the Earth, announcing itself with nothing more than a steady, simple radio pulse. That faint heartbeat circled the globe, echoing through radios and living rooms, telling the world that the Soviets had opened a door no one else had yet touched. Its battery survived only a few weeks, and the little satellite fell soon after, but its presence changed the shape of history. Another followed, carrying the first living creature ever sent into orbit, a small dog who never returned, circling the Earth for months before falling back into fire. Then came the third, a heavier vessel, loaded with instruments meant to taste the radiation and cosmic particles beyond the sky. For years it circled above us, long after its voice had gone quiet, a metal shadow gliding along the edge of night. Soon the sky filled with names like Cosmos, Vostok, Luna, and Molnia. Some were meant for science, others served purposes hidden behind locked doors. Many slipped into low or medium orbits, completed their missions, and were left there no fuel to return, no instructions to follow. The Cosmos line alone numbered in the hundreds, a forest of metal whose stories were often classified or disguised. Some were test beds, some carried instruments that watched the Earth, some hid darker experiments behind neutral names. They rose secretly, tracked only by distant radar, and their paths were written into files never meant for public eyes. Among them were spacecraft intended for the moon. Not all made the journey. Some faltered moments after launch. Others orbited Earth instead of escaping it. becoming accidental ghosts machines built for grander horizons, now trapped in quiet circles close to home, without guidance, without power, left to drift from the moment they were born. Soon after, the Soviets began launching the vessels that would one day carry cosmonauts. Before sending any human into the unknown, they tested these capsules with unmanned trials. Some never reached proper orbit. Others completed their loops, passed their tests, and returned. A few remain above us, trapped between Earthlight and darkness. Among the more unusual relics are the radar ocean reconnaissance satellites, machines that carried compact nuclear reactors to power their hungry instruments. Once their missions ended, they discarded their cores into orbits far above, leaving their bodies behind in lower paths. They glide there still, silent but heavy with memories of the materials they once held. There were the Molniya satellites too, moving in long, stretched ellipses that climbed high above the Arctic regions before sweeping close again. Their odd orbits allowed a nation spread across northern latitudes to stay connected, and many of these elongated travelers remain looping and looping through time. Tracking these old relics has never been simple. Many were launched under secrecy. Some had their flight paths altered. Others drifted unpredictably as years passed. Modern radar works patiently to rediscover and name them, though their silence makes them hard to find. Hobbyists, watching the night sky with nothing more than small telescopes and persistent curiosity, have spotted many of these forgotten wanderers, catching faint streaks of light as metal bodies sweep across starlight. Above us, the remnants of that rivalry still linger. Machines built under pressure and ambition continue their quiet circuits. They have no purpose now, no voice, no crew, yet they endure, suspended between memory and oblivion. Among these relics is the first home humans ever built in space. A long, metal chamber launched in the spring of 1971, meant to hold life for weeks, even months. It was small, narrow, and simple by today's standards. But it was the beginning of an idea, a place where people could live, sleep, work, and dream far from Earth. The crew that first attempted to enter it could not dock. They reached out, brushed past, felt the station through their gloves, but the mechanism refused to lock. They returned to Earth untouched by the home waiting for them. Later, another crew succeeded. They floated inside that cramped cylinder, becoming the first people to truly live beyond our world for more than a few breaths. For nearly a month, they watched Earth spin below, studied their own bodies as they changed in weightlessness, tested equipment, and greeted each sunrise from the other side of the atmosphere. They did not know that their mission would end in sorrow. On their return journey, a valve opened too soon, and the air slipped from their capsule in the silence of space. By the time their craft touched Earth, life had already left them. The station they had lived in continued to circle the planet, empty now, a hollow shell holding echoes of footsteps and soft voices. Engineers guided it to a final descent months later, letting it fall in a controlled arc over the ocean, where most of it burned away in a brief, bright moment. Only fragments may remain, tiny pieces drifting unseen among the cloud of debris around our planet. But the design survived, becoming the foundation for the stations that would follow. Lessons learned in grief reshaped spacecraft, made safety stricter, and changed what humanity dared to attempt next. The station drifted for less than half a year. Only one crew ever breathed inside it. But its influence lingers in every modular piece of hardware that orbits Earth today. Every sealed suit worn during launch, every safety system built to protect a crew. Some ghosts in space are metal, some are memories. This one is both. And then there was America's own early home in orbit, a broad, cylindrical laboratory built from the bones of moon rockets. It was spacious for its time, warm with sunlight through its wide windows, carrying the hope that people could stay above the world for longer than ever before. Yet even this station lived only briefly. Its final descent, written not by engineering, but by shifting budgets and the slow pull of Earth's upper air. Soon after its launch, the station suffered tears and failures. Shielding ripped away, solar panels lost, temperatures soared. It seemed almost lost before it had truly begun. But a small crew lifted off 10 days later, carrying tools and a fragile sunshade they stretched across the wounded exterior. With care and patience, they cooled its burning interior and brought it back to life. More crews followed, staying for longer stretches, studying the sun, the earth, and their own changing bodies. They proved that long stays in space were possible, even productive. But while they worked, time was quietly undoing the station's future. The shuttle that was meant to revisit and rescue it was delayed year after year. Meanwhile, the Earth's upper atmosphere, heated by an unexpectedly restless sun, expanded upward, brushing the station with enough resistance to draw it downward faster and faster. By the time NASA understood how quickly the orbit was dropping, nothing could reach it. The shuttle was unfinished. No rockets were ready. The station's fall was inevitable. The only question was when and where. For a long stretch of months, the station's slow descent was watched with a kind of hushed vigilance. Its path wavered with every thin breath of the upper atmosphere, and NASA tried gently to predict the moment when it would fall. Notices were sent across the world, soft warnings carried between agencies and governments, all hoping the great metal shell would break apart over empty sea. But the sky had its own quiet timing, and no calculation could hold it still. On the 11th day of July in the year 1979, the station finally slipped into the thick air of Earth. High above the Indian Ocean, the structure began to glow, then splinter. Fragments of metal and tanks and panels arced across the dark, pulled down in a wide streak that brushed over the lonely spaces of Western Australia. Most of the pieces vanished in fire, but some survived the long fall, scattering through quiet stretches of desert where no one was harmed. For a brief moment, the whole world looked upward as news spread of the largest uncontrolled descent of a human-made object in history. People found fragments lying half buried in the red sand, sun-warmed and silent. A small Australian town jokingly issued NASA a fine $400 for leaving debris behind. Souvenir hunters gathered pieces, some of which still rest in private collections or small museums. And though most of the station dissolved in its fiery return, a few remnants may still sleep where they landed, worn by time but not erased. That fall revealed something larger than the fragments themselves. The quiet risk that comes with placing great structures in orbit without a plan to bring them home. Unlike the earlier Soviet station, which was guided gently to its end, this one had no way to steer itself, no engines to adjust its fate. The lesson stayed with NASA. Later missions, including the International Space Station, were shaped with careful thoughts toward orbit management and safe descent, born from the memory of the Great Falling Lab. In those years, the technology was still new, and much was being learned moment by moment. The station had no successor, no improved twin rose after it. It stood alone, built from the leftover bones of the Apollo era, an attempt to create something bold from the tools already in hand. By the time the space shuttle finally flew in the early 1980s, the station had already broken apart in the sky. They missed each other by only a small handful of years, two dreams passing in opposite directions, and yet, its short life created a bridge, one that showed humans could live above Earth not for days, but for months. And that large, livable structures could be built where there is no air and no up or down. Even in its fall, it left a soft trail of understanding behind. Far away from Earth, where nothing moves unless struck, the Soviet lunar landers remain untouched. They sit on the quiet surface of the moon, beneath a sky that never clouds, never storms, never shifts. These small machines, left more than half a century ago, remain exactly where they settled. Dust gathers slowly, not from wind, but from time alone. Under that stillness lies the story of one of humanity's earliest attempts to understand a world beyond its own. The lunar program began in the tense years of the late 1950s, when the United States and the Soviet Union raced to reach deeper into the cosmos. While American plans were still circling Earth, the Soviets were already sending probes toward the moon, some meant to crash into its surface, others hoping to land softly. There were many failures at first. Some rockets faltered before clearing the sky, others fell back to Earth or slipped into the wrong path. But each failure whispered something useful to the engineers who listened. With every attempt, the designs grew stronger, more precise, more ready. In the year 1959, Luna 2 struck the moon and became the first human-made object to touch another world. Soon after, Luna 3 swept past the far side, sending back the first pictures ever taken of regions no earthbound eye had seen. These early missions were brief, but they proved that the moon could be reached. Then came Luna 9 in the year 1966, the first probe to touch the surface gently. It landed using retro rockets and airbags, settling like a careful seed falling onto quiet ground. Its metal petals unfolded to reveal a small camera that captured a landscape of stillness, flat dust, scattered stones, and a sky so black it looked endless. For the first time, humanity saw what it felt like to stand on the moon. In the years that followed, more landers arrived. Luna 13 with better instruments, Luna 16, 20, and 24, which drilled into the soil and returned precious samples to Earth. These were early robotic explorers, guided by primitive computers, yet capable of work still admired today. They operated for days or weeks before the bitter lunar night stole their warmth and froze their circuits. When their power faded, their voices faded too, never to return. The moon offered no mercy, yet it preserved their bodies. With no atmosphere to erode them, the landers remain almost unchanged. Metal frames cracked from cold, panels faded, but otherwise untouched across decades. They are time travelers in place, sitting exactly where they last breathed. Some carried rovers, little mechanical creatures called lunocods, meaning moonwalkers. The first, Lunacod 1, touched the surface in the year 1970. Driven from Earth with a few seconds of delay, it crawled across the landscape, leaving tracks that remain there today. In photographs taken later by NASA's orbiting camera, those tracks can still be traced, dark lines woven into the pale dust. The last mission of this long chapter was Luna 24 in the year 1976. It scooped a slender core of soil 170 grams before returning home. After that, the Soviets turned their attention to other worlds. The moon grew quiet again, and the machines already resting there were left to the timeless cold. Modern, high-orbit cameras have rediscovered many of them. Their shadows fall exactly where they fell decades earlier. Their shapes are faint but familiar. The rover tracks remain unbroken. Everything sits in a silence so deep, it almost feels like reverence. From these early attempts came the lineage of today's explorers, rovers on Mars, landers on asteroids, probes that sail around distant giants. All of them trace their origins to the fragile machines the Soviets sent across the Gulf with wires, gears, and hope. Not all worlds greet visitors gently. Some crush, melt, and consume everything that tries to meet them. Venus is such a place hot enough to soften lead, cloaked in clouds that bite like acid, and wrapped in an atmosphere so heavy it presses with the weight of deep ocean water. Reaching Venus has never been the hard part. Surviving it has. The Soviets tried anyway. Their Venera missions took shape in the early 1960s, reaching for a planet that gleamed softly in Earth's twilight sky. At first, no one knew its true nature. Some imagined warm oceans and dense, humid air. The earliest probes did not last long enough to answer. Many failed at launch. Some lost contact before they even crossed the gap between planets. But, little by little, engineers learned to strengthen their travelers. Venera 4, in the year 1967, dipped into Venus's atmosphere and sent back the first hints of the truth. Air thick with carbon dioxide, clouds laced with acid, heat rising beyond all early expectations. It did not reach the ground. The pressure crushed it. But from its brief descent, humanity learned that Venus was not Earth's twin, but Earth's burning shadow. Venera 7 arrived 3 years later, built with walls like armor and a shortened parachute to rush its fall. It touched the surface and lived for a handful of minutes, 23, sending the first message ever spoken from the surface of another planet. The heat grew too severe, and its circuits surrendered, but it had already changed history. Others lasted longer. Venera 8 for 50 minutes. Venera 9 and 10 returned the first photographs of the Venusian ground flat stones under a hazy, orange glow that passed for daylight on that world. The images were grainy, but profound. Each landing was a race against time. The moment a probe touched down, the planet began unmaking it. Temperatures soared to nearly 470 degrees Celsius. Written out as 470 degrees Celsius, pressures climbed more than 90 times that of Earth, and the acid-laced air chewed at metal. Cooling tanks warmed, electronics bent, wires softened. One by one, systems failed, and still, the missions continued. Venera 13 in the early 1980s survived for more than 2 hours, sharing the first recorded sounds from another planet: the rush of wind, the whispering hiss of thick air, and the faint hum of its own machinery struggling to endure. Venera 14 followed, sending back its own visions before succumbing. Later craft Venera 15 and 16 stayed in orbit, mapping the world with radar. Since no camera could pierce the clouds from above, their work traced the surface through signals, painting landscapes without light. None of the landers remain intact. Unlike the quiet relics on the moon, these machines were undone where they stood. Their shells warped, their circuits melted, their frames possibly crushed into the burning ground. Venus hides its dead beneath a veil so dense that no eye has ever looked upon their remains. Only data, photographs, and a few seconds of sound have endured. Yet their story is not one of failure. They pushed deeper into danger than any machine before them. They taught engineers how to design for the unendurable. They carried back truths from a world that resists understanding. Even today, modern missions still turn to their data, their courage folded into the plans for new orbiters that will one day return not to stand on the surface, but to watch from above, learning through radar and distant sensing rather than direct contact. For now, the Venera landers remain beyond our reach. No camera can peer through the permanent clouds to see what is left of them. They were ghosts forged in fire, machines that sank into a world that burns and never came back. For a brief time, they spoke to us from the surface of that hidden, violent planet, the first and so far the only voices ever heard from there. Their last messages crossed the darkness like sighs, and then the line went still. Farther out, beyond the orbit of Mars, another kind of pioneer was already on its way. In the early 1970s, two small spacecraft rose from Earth with a quieter, farther dream. They were called Pioneer 10 and Pioneer 11, early scouts sent by NASA toward the outer reaches of the solar system. They were simple by today's standards, all metal frames and exposed instruments, but their destination was a place no human-made object had ever tried to reach. Pioneer 10 left first, in early March of the year 1972. Its main task was both straightforward and astonishing. Travel all the way to Jupiter, slip through its fierce radiation belts, and send back close photographs and measurements. Until then, the giant planet had only ever been seen through telescopes as a distant disk of shifting bands and storms. Pioneer 10 crossed the Gulf of Space in just under 2 years, coasting toward a world made mostly of cloud. In early December of the year 1973, it swept past Jupiter at a distance of roughly 132,000 kilometers above the tops of its clouds. From that vantage point, it captured the swirling storms, the glow of charged particles in the planet's magnetic field, and the pale glints of its moons. It survived a passage through radiation so intense it could have crippled its electronics, then emerged on the far side, its primary mission complete. But nothing waited to pull it back. With no more major planets in its path, Pioneer 10 simply kept going. Launch had given it a certain momentum, and gravity guided that momentum into a long, straight path. It slipped past the orbit of Saturn, then Uranus, then Neptune, heading slowly out of the thin disk where most planets reside, angling toward the direction of the constellation Taurus. There were no thrusters left to steer, no fuel to waste on course changes, only a quiet glide into deepening darkness. Pioneer 11 followed a year later, in early April of 1973. Its journey began similarly, with a flight past Jupiter in the year 1974. But mission planners used Jupiter's gravity like a sling, bending Pioneer 11's path towards Saturn. No one had ever used this kind of planetary assist in such a way before. In early September of 1979, Pioneer 11 became the first machine to visit Saturn, diving to within about 21,000 kilometers of its cloud tops. It took the first close images of the planet's rings, confirmed its strong magnetic field, and revealed details of its moons. Both spacecraft were tough but modest. Their instruments were designed in the 1960s. Their memory was measured in only a handful of kilobytes. Yet they worked, and when their encounters were over, they did the same thing their sibling did. They sailed onward into the deep. As the years passed and the distance grew, their signals faded. What had once been strong transmissions became barely audible whispers. NASA's huge radio antennas strained to hear them across the widening gulf. Pioneer 11 fell silent first. In the mid-1990s, contact was lost. It had been heading out toward the constellation Scutum. Its power ran down, its systems dimmed, and finally there was nothing left to hear. The spacecraft itself did not need power to keep flying. It simply drifted away, dark and unseen. Pioneer 10 held on a little longer. Its final confirmed signal reached Earth in late January of the year 2003. By then, it was more than 12 billion kilometers from home. The radio call took more than 11 hours to cross the emptiness, arriving as a faint murmur buried in cosmic static. After that, no further contact could be made. Yet Pioneer 10, like its twin, did not stop. It continued outward, its path carrying it through the far reaches of the heliosphere, the great bubble carved by the sun's wind toward the even deeper sea of interstellar space. It will take thousands of years for these small craft to truly enter that realm where the pressure of other stars' winds exceeds our own sun's. Beyond that, tens of thousands, even millions of years will pass as they wander. Pioneer 10 is roughly aimed toward a small red dwarf star called Ross 248 and may pass somewhat near it in around 2 million years. But it will not escape the Milky Way. Gravity will one day curve its path into a long, slow orbit around the galaxy, binding it as a silent passenger for ages beyond any human history. Each pioneer carries a tiny message on its side, a gold-colored plaque of anodized aluminum bolted onto the frame. Designed by Carl Sagan and Frank Drake, with artwork by Linda Salzman Sagan, the plaque shows two human figures, one man and one woman, drawn as simple outlines. Behind them stands the spacecraft itself for scale. Etched into the metal is a map of sorts, a pattern of lines pointing to pulsars, unique cosmic beacons whose signals could, in theory, help an outsider locate our Sunday. There is a drawing of the solar system with the pioneer's path traced outward. The plaque does not help the mission function. It is not an instrument or a shield. It is a greeting, a quiet note from a small world circling a modest star, sent out in case it is ever found. The odds of anyone or anything discovering it are so tiny that they are almost beyond comprehension. Space is too wide, too sparse. Even after 1 million years, the craft might never pass near another star. But the message rides along anyway, just in case. In the vacuum, the spacecraft themselves likely remain largely intact. There is no air to rust them, no water to corrode them, no wind to sand them down. Their metal has cooled to near the coldest temperatures nature allows. Inside, circuits and wires sit frozen as if held mid-thought. The radioactive power sources that once glowed with heat have dwindled to almost nothing. The gold plaques may still gleam in whatever faint starlight touches them, unchanged as the galaxy turns. That we built these tiny machines with the technology of the 1970s and sent them so far, and that they are still traveling, says something about the quiet endurance of human imagination. They were constructed under budgets and schedules that now seem modest, yet their journey has outlasted plans, careers, and even many of the people who first assembled them. Not long after the pioneers departed, another pair of travelers followed, carrying not only instruments, but music. In the soft light of late summer, in the year 1977, 2 more spacecraft rose from Earth, Voyager 2 first, and then Voyager 1 a few weeks later. They carried cameras, spectrometers, magnetometers, and a host of sensors meant to reveal the outer planets in detail no one had ever seen. But bolted to each one was also a golden record, a round metal disc containing sounds and images from Earth, a fragile greeting meant for whatever might one day find it. The Voyagers built on the pioneers' achievements, but their ambitions stretched farther. They launched during a rare alignment of the giant planets, an arrangement that happens only once every roughly 176 years. This allowed them to use gravity assists, skimming past one world to steal a bit of its motion and fling themselves toward the next. Voyager 1 visited Jupiter and Saturn. Voyager 2 made the full tour: Jupiter, Saturn, Uranus, and Neptune, becoming the first and only spacecraft so far to see those last 2 worlds up close. At each encounter, they showed us things no telescope on Earth could: volcanoes erupting on Io, delicate rings and intricate storms around the giant planets, strange icy moons lit by distant sunlight. They traced invisible magnetic fields and tasted the thin plasmas that surround those worlds. Then, as with the pioneers, the planets fell behind them. Their primary mission ended, but their flight did not. By the early 1990s, the Voyager's grand tour was over. Yet there was still power in their nuclear generators. Engineers on the ground slowly reconfigured their systems, turning off some instruments to keep others alive. The spacecraft continued to report on the environment far from the Sunday. Their signals, though faint, were still caught by the Deep Space Network, vast radio telescopes on Earth that listen for whispers from afar. In the year 2012, Voyager 1 crossed a boundary called the heliopause, where the sun's influence gives way to the thin pressure of interstellar space. It became the first human-made object known to have entered that region. Voyager 2 followed a similar path, crossing the same frontier in the year 2018. They now drift between the stars, sampling particles, fields, and waves in a place no other machine from Earth has ever touched. Each year, their power weakens. Their plutonium-based generators grow colder, and mission controllers must choose carefully which systems to keep alive. One by one, instruments are shut down so that a few can keep working. The heaters that protect the electronics fail in some parts of the craft, yet the hardware sometimes continues to function in temperatures it was never designed to endure. Signals from Voyager 1 now take more than 22 hours to reach Earth, arriving as radio waves weaker than a whisper buried in cosmic noise. It is like trying to hear a watch tick from across a continent. Yet within that faint signal is information about cosmic rays, magnetic fields, and the structure of space itself. No other mission has gone so far for so long. When the last watt of power fades, the Voyagers will fall silent, but they will not stop. Like the pioneers, they will continue to travel, dark and quiet, long after our descendants have forgotten the languages in which their commands were written. The golden records they carry are about the size of a classic long-playing vinyl album, made of gold-plated copper and mounted behind protective covers. Etched onto the cover is a diagram: how to play the disc, what speed to spin it, how to decode the images, and a simple map to our Sunday. On the records themselves are greetings in dozens of human languages, the sounds of wind, rain, waves, and thunder, the chirping of birds, the rumble of trains, and the quiet rhythm of a heartbeat. There are pictures of mountains, forests, cities, and families. There is music from many traditions, Bach and Beethoven beside folk songs from Bulgaria, chants from Navajo singers, flutes from Japan, rhythms from Senegal and Peru, a raga performed by Indian sitar master Ravi Shankar. The idea was not to say, here is our technology, but here is what it feels like to be us. Carl Sagan once likened the record to a bottle cast into the cosmic ocean, not aimed at anyone in particular, but set adrift as a sign that someone once lived here and cared enough to say hello. A brief message from President Jimmy Carter was included as well, speaking of a small world trying to survive its own time in the hope of living into someone else's. The chance that another intelligence might one day find and understand these records is unbelievably small, but for as long as the discs survive, they carry a snapshot of Earth in the late 1970s. Our sounds, our images, our struggles and joys, locked into grooves of metal, spinning through the dark. Not every spacecraft stays near planets or travels out of the solar system's plane. Some follow stranger, more intricate paths, looping between worlds and turning old missions into new ones. In the late 1970s, a satellite was launched that was never meant to chase comets at all. It was called ISEE-3, the third in a series known as the International Sun-Earth Explorer. Alongside its sister spacecraft, it was meant to study the solar wind, the stream of charged particles flowing from the sun, and the way it interacts with Earth's magnetic shield. Positioned near a point called L1, about 1 million miles sunward from our planet, it became the first spacecraft to orbit around a Lagrange point where the gravity of Earth and Sun balance in a delicate way. For several years, ISEE-3 watched the invisible weather between us and our star, recording changes in magnetic fields and currents of plasma. It was a quiet, steady job, and the spacecraft performed it well, living longer than anyone had first expected. By the early 1980s, it had already exceeded its planned lifespan. Many missions would have ended there. Instead, its story took an unexpected turn. Engineers realized that the little craft still had fuel and functioning instruments. They imagined something bold. Why not send it to meet a comet? To do that, they would have to reshape its orbit entirely, using the moon's gravity to fling it into a new path around the Sunday. Step by step, they planned a series of close lunar flybys, each one tugging the spacecraft farther away from its comfortable perch. As it departed, it passed one last time through the long magnetic tail that stretches behind Earth, gathering a final set of measurements from its original assignment. Then, in the year 1983, its name was changed from ISEE-3 to ICE, the International Cometary Explorer, a rare moment when a satellite designed for one task was officially reborn for another, already far from home. Its new target was a modest comet called Giacobini Zinner, not bright like Halley's, not famous, but placed on an orbit the spacecraft could reach. On the 11th day of September, in the year 1985, ICE flew through the delicate tail of that comet, tasting the dust and charged gas streaming away from its nucleus. In doing so, it became the first spacecraft in history to do so. The encounter revealed how a comet's tail breathes, how dust and charged particles stream behind it, how the solar wind sculpts it, and how quickly those tiny grains race through the dark. The International Cometary Explorer slipped through that pale wake and emerged still alive, still working after so many years, as if its small metal body had learned to endure whatever space placed before it. Afterward, it drifted onward, quiet and steady. In the year 1986, it passed near Halley's Comet, though not close enough for dramatic pictures like the European Space Agency's Giotto. Even so, it measured the solar wind from afar, helping scientists understand how Halley's long tail spread and bent under the sun's breath. Its instruments kept murmuring their data back toward Earth for years, even though no one expected more comet encounters. Only in the late 1990s did NASA finally end official contact. Yet the spacecraft itself did not die. It simply continued drifting, like an old worker who keeps walking long after the shift has ended. Then, many years later, something remarkable happened. In the year 2014, a small group of citizen scientists and engineers calling themselves the ISEE-3 Reboot Project noticed that the craft's long orbit would bring it near Earth again. They wondered if it might still listen. With crowd-funded support, they studied old documents, traced forgotten wiring diagrams, and searched for any surviving equipment that could speak its radio language. The hardware NASA had once used was gone, but the group found a willing partner in a great dish antenna at the Arecibo Observatory in Puerto Rico. They sent a call across the void. To their astonishment, the spacecraft replied. After roughly 36 years in space, the International Cometary Explorer still heard its name. For a moment, the past opened its eyes. The team hoped to nudge its orbit, perhaps waking it into a small new mission studying solar wind again, or sampling the space weather near Earth. But when they attempted to fire its thrusters, nothing happened. Analysis suggested that the nitrogen pressurant needed to push fuel through the engine lines had leaked away over the decades. The craft still had strength in its heart, but no breath left to move. It could listen, but not steer. Still, the moment mattered. For a short while, a forgotten spacecraft spoke again. The team gathered what data they could, listened to the final fading transmissions, and watched as the small craft drifted past Earth and slipped once more into its long orbit around the Sun, an orbit it may follow for centuries. The International Cometary Explorer's story is a quiet one. It began by watching the Sun, then turned toward a comet. It crossed scientific fields, adapted mid-flight, and became something its designers never expected. It had no golden record, no iconic photographs, and most people have never heard its name. Yet it was the first to orbit a Lagrange point, the first to fly through a comet's tail, and the first old mission revived by citizens rather than a space agency. Now it moves unseen, one more gentle ghost in the solar system, still whole, still circling, its solar panels catching sunlight that no longer powers anything at all. And beyond that lonely orbit lies another world, one that taught engineers the meaning of silence, long before rovers and helicopters traced their first paths across its dust. Mars, now familiar through the eyes of modern explorers, was once a place where dreams went to vanish. Early missions attempted to touch it, but most never managed more than a whisper, if that. Some died trying to leave Earth. Some fell mute between planets. Others possibly survived descent only to fade before sending a single clear word. The story of failure at Mars begins with the earliest attempts in the 1960s and 1970s, when the Soviet Union launched a succession of large, ambitious craft under the Mars program. Built with the technology of their era, heavy metal frames, early electronics, imperfect guidance, they faced a world far less forgiving than Earth. Reaching Mars is difficult. Entering its orbit is harder. Landing is harder still. But the hardest task of all is speaking afterward. Mars 1, launched in the year 1962, left Earth successfully, but lost contact when it was roughly 100 million kilometers away. A leak in the orientation system is thought to have slowly turned the spacecraft until its antenna no longer pointed home. Even now, it likely loops around the Sun in silence. Mars 2 and Mars 3, launched together in the year 1971, carried orbiters and landers. Mars 2's lander entered the atmosphere too steeply and crashed without a word. Mars 3's lander touched down gently. It was the first soft landing on Mars in human history, but its signal lasted only about 14.5 seconds before it ended forever. A dust storm? A fault? Perhaps both. No one knows. For decades, no one even knew where Mars 3 had fallen. Then, in the year 2013, careful eyes examining high-resolution images from NASA's Mars Reconnaissance Orbiter spotted shapes that matched a parachute, a heat shield, and the silent lander itself. But even with its resting place known, its silence remains absolute. It touched Mars and died in the same instant. Mars 4 and Mars 5 launched soon after in the early 1970s. Mars 4 missed orbit and flew past the planet. Mars 5 reached orbit, but stopped communicating after a few days. Mars 6's lander sent data during descent until its final moment, when it struck the ground and went dark. Mars 7's lander never even entered the atmosphere. A mechanical fault let it drift aimlessly past the planet. Each mission carried hope, and each left behind only quiet. The United States faced its own challenges. Before the success of the Viking landers, the Mariner program learned painful lessons. Mariner 3 failed to leave Earth because of a shroud malfunction. Mariner 8 also fell short, plunging into the Atlantic. Only Mariner 9 succeeded, becoming the first spacecraft to orbit another planet. NASA's Mars Observer, launched in the year 1992, was meant to study the surface and atmosphere in detail. But days before orbit insertion, it vanished. A fuel line rupture is the likely cause. No signal ever returned. The late 1990s brought more heartbreak. The Mars Climate Orbiter, carrying instruments and acting as a relay for another lander, was lost because teams used different measurement units, one metric, one imperial. A simple human oversight sent the craft fatally low into the atmosphere. Months later, the Mars Polar Lander disappeared during its descent. Evidence later suggested it may have shut off its engines prematurely, believing it had touched the ground when it was still high above it. Two small impact probes that rode along, called Deep Space 2, also never spoke. Even modern missions are not immune. India's Mars Orbiter mission, a triumph when it entered orbit in the year 2013, eventually fell silent in the year 2022, likely after running out of fuel during a difficult solar eclipse alignment. Each failure taught something. Each piece of lost metal carried a lesson home. Engineers studied every silence, every missing signal, every faint trace. Mars is a world that punishes haste. Its thin air makes parachutes unreliable. Its rocky slopes are unpredictable, and its long communication delay means that every landing must succeed without human intervention. Among the most haunting failures are two European missions that became symbols of how close success can come to collapse. The first was Beagle 2, a small lander named after the ship that carried Charles Darwin. It rode with the Mars Express orbiter and was designed to unfold on the surface like a mechanical flower in Isidis Planitia. It was Europe's first attempt at a Mars landing, and also a source of pride in the United Kingdom. It carried cameras, a robotic arm, sampling tools, and even a small microphone. Beagle 2 was set to land on the 25th of December in the year 2003, but its voice never reached Earth. For more than 11 years, no one knew what had happened. Then, in the year 2015, images from the Mars Reconnaissance Orbiter revealed the truth. The lander was intact, resting gently on the surface, but only some of its solar panels had opened. A single panel trapped the antenna beneath it. Beagle 2 had succeeded in everything except unfolding completely. The second was Schiaparelli. In the year 2016, part of the ExoMars mission. It descended correctly at first atmospheric entry, parachute deployment, heat shield separation, all worked. But a sensor glitch caused the craft to believe it was below ground level when it was still far above. It shut down its engines early, released its parachute, and fell freely. Orbital images later showed the impact, mark, and scattered pieces. These failures deepened the myth of a Mars curse, though the truth is simply that Mars demands perfection. Before perseverance and curiosity, spirit and opportunity, and the small helicopter ingenuity, there were many missions that tried and failed. Beagle 2 and Schiaparelli still lie on the Martian surface, silent, dust-touched reminders of hope, effort, and the fragile line between success and silence. And now, alongside them, new machines roam and fly, tracing fresh marks across a world that has tested human resolve for more than half a century. The path to success on Mars was lined with these quiet losses. The planet did not welcome visitors gently. Each lander that fell short left behind data, questions, and a small clearing in the dark, making the way just a little more certain for the next machine that tried. Far closer to the sun, another world waited in near silence. Mercury feels almost unreal when you imagine it. The innermost planet is scorched on one side and frozen on the other. Sunlit ground can reach roughly 420 degrees Fahrenheit, while nearby shadowed regions fall far below freezing. There is no comforting blanket of air, only a thin exosphere of scattered atoms. The planet is small, dense, and hammered constantly by the sun's radiation. From afar, it gleams like a bright metal plate left out in a desert of light. For a long time, Mercury was mostly a mystery. Telescopes on Earth struggled to see it clearly because it sits so close to the sun's glare. Only one visitor, Mariner 10 in the 1970s, had ever flown by, and it managed to map less than half of the surface. Then, for decades, there was nothing. Messenger changed that. Launched by NASA in the early 2000s, Messenger, short for Mercury Surface, Space Environment, Geochemistry, and Ranging, was the first spacecraft ever sent to orbit Mercury itself. Reaching it was not as simple as falling inward. The closer you get to the sun, the faster you move. And to be captured by tiny Mercury's gravity, a spacecraft must give up an enormous amount of speed. Traditional engines alone could not easily do this without carrying impossible amounts of fuel. So the journey had to be slow and clever. Messenger spent about 7 years weaving through the inner solar system. It flew once past Earth, twice past Venus, and 3 times past Mercury, before it had lost enough speed to be gently caught. Each flyby bent its path and drained a little velocity, like a stone skipping across a pond and losing energy with each touch. At last, in early 2011, Messenger slid into orbit. Once settled, it circled Mercury roughly twice a day. Its instruments began to peel back the planet's secrets. Cameras revealed a scarred surface full of ancient craters, but also odd, bright patches and strange, shallow depressions called hollows. These features hinted that Mercury was not a fully dead world, but one that had seen activity more recently than anyone expected. One of the most surprising discoveries hid at the poles. Because Mercury's axis is almost perfectly upright, some craters near the poles never see sunlight at all. In those permanent shadows, Messenger found regions bright to radar in a way that matched deposits of water ice. The closest planet to the sun, harboring frozen water in dark pockets that never warm, it felt like a paradox. Yet, the geometry of light and shadow made it possible. Messenger also helped explain why Mercury is so dense. The planet has an enormous iron core relative to its size. One idea had long suggested that, early in its history, a massive collision might have stripped away much of its outer layers, leaving behind a metal-rich remnant. By measuring the elements on the surface, Messenger found evidence that Mercury had endured intense heat and a violent past, supporting the picture of a world forged and perhaps reshaped in extremes. Around the planet, Messenger studied a small but active magnetic field, watching how the solar wind battered and squeezed it. Unlike Earth's broad, sheltering magnetosphere, Mercury's is cramped and constantly shoved around by the Sunday. Messenger recorded bursts of charged particles and brief magnetic reconnection events, tiny explosions in space, where field lines snap and reform, flinging particles outward. Year after year, the spacecraft traced these patterns, building a detailed portrait of a world that had once been little more than a bright speck in the sky. It circled Mercury thousands of times, sending home hundreds of thousands of images and streams of data. But fuel does not last forever. Without propellant to adjust its orbit, Messenger's path slowly dipped lower. Mercury's pull and the constant pressure of sunlight drew it down, bit by bit. Engineers stretched the mission by using every last resource. Even the helium gas, meant only to pressurize the fuel system. Eventually, there was nothing more to spend. In late April of the year 2015, Messenger struck Mercury's surface at tremendous speed. No one saw the impact directly. The signal simply ended at the predicted moment, and in that quiet cut, the mission was over. Somewhere near a region called Shakespeare Basin, the spacecraft carved a small new crater into the dust. No other probe has yet gone back to photograph it. Messenger had worked alone. There were no companion orbiters, no landers waiting below, no backup mission arriving later. Its crash was both an ending and a punctuation mark. Mercury fell silent again, keeping its newly revealed secrets locked in rock, while the only trace of the spacecraft's presence was the data stored back on Earth and a tiny unseen wound on an airless world. For a while after Messenger's fall, there were no eyes at Mercury at all. The planet spun on, sunburned and quiet. Only much later would a new mission, Bepi Colombo, begin its own long journey inward, aiming to arrive in the later 2020s. Until then, Mercury remains alone, its lone orbiter reduced to dust. Farther out, in the wide belt between Mars and Jupiter, another explorer followed a softer, more lingering path. Dawn was launched in the late 2000s with an unusual assignment. Instead of visiting just one world, it was built to orbit two Vesta and Ceres, the two largest bodies in the asteroid belt. These are not small, shapeless rocks, but ancient survivors from the dawn of the solar system. Each carries a different record of how planets tried, and sometimes failed, to form. To make such a journey possible, Dawn relied on ion propulsion. Unlike roaring chemical rockets that deliver a short, fierce push, ion engines exhale a faint, constant stream of charged particles. The thrust is gentle, almost a whisper, but it can be sustained for months or years. Over time, that soft push adds up, allowing a spacecraft to slip into and out of orbits in ways that would otherwise be impossible with limited fuel. Vesta was Dawn's first destination. When the spacecraft arrived after several years of flight, it found a world that looked battered, yet intricate. Vesta's shape was lopsided and scarred, dominated by an enormous impact basin near the South Pole Resilvia, so wide and deep that it seemed to have nearly shattered the body. The force of that collision likely flung pieces of Vesta across the solar system. Some of the meteorites that fall on Earth today are thought to be fragments chipped from its crust long ago. Dawn mapped Vesta in careful detail. It found signs of an internal structure with layers, a crust, mantle, and core more like a tiny protoplanet than a simple chunk of rock. Ancient lava flows, deep grooves, and carved troughs told a story of early heat and partial melting. Vesta seemed to be a world that had once been on its way to becoming a small planet, but whose growth had been cut short. After more than a year, Dawn gradually loosened itself from Vesta's gravity and drifted away, turning its gentle engines toward Ceres. Ceres is different in almost every way, rounder, darker, and less dense, with a higher content of water-bearing minerals. When Dawn arrived, it saw a muted, gray surface with subtle variations. Then bright specks appeared in its images, gleaming spots inside certain craters. The most striking lay inside a depression called Ocata. From afar, the spots looked like splashes of light, on dark ground. As dawn spiraled closer, the bright regions resolved into deposits of reflective salts, particularly sodium carbonates that seemed to have seeped up from below. This suggested that Ceres once had, and perhaps still has, pockets of salty liquid hidden beneath its crust. The dwarf planet's surface also showed domes, fractures, and hints of cryovolcanism, cold volcanoes that ooze water or mud instead of molten rock. One lonely mountain, Ahuna Mons, rose smoothly above the plains, like a frozen bubble of material pushed up from inside. It may be relatively young, a sign that Ceres is not entirely dormant. Dawn shifted its orbit several times, sometimes circling high to map the globe, sometimes swooping down low enough to see individual boulders and subtle changes in texture. It had no lander, but it drew an intricate map that future missions might one day use to choose safe landing sites. All the while, its hydrazine fuel, the liquid used to control its pointing, slowly dwindled. Solar panels gave Dawn electricity, even out in the dimmer sunlight of the asteroid belt, but they could not replace the propellant that aimed its instruments and antenna. By late 2018, mission planners knew the end was approaching. Dawn would not crash. Instead, they placed it in a stable orbit around Ceres, one that should remain safe for a very long time. The last of the hydrazine was spent on carefully planned maneuvers. When the fuel finally ran out, the spacecraft lost the ability to point toward Earth. Its transmissions stopped. Now Dawn's body still circles Ceres silently, a dark shape above a cold, shadowed world. It will likely remain there for decades or centuries, a quiet guardian that can no longer report what it sees. In its wake, it leaves a rich legacy, the knowledge that Vesta and Ceres are not merely debris, but fossils from the solar system's earliest chapter. One is dry and rocky, the other icy and soft, each frozen at a different moment in time. Even farther out, beyond Mars, another mission chased something far more ephemeral, a comet, icy and fragile, and alive in its own slow way. Rosetta began its journey in the year 2004, launched from the equatorial forests of French Guiana. Its goal was not just to glance at a comet, but to catch one to match its orbit, travel alongside it, and eventually set a small lander on its surface. The chosen target was Comet 67P, Churyumov-Gerasimenko, an object of ice and dust that circles the Sun in a roughly 6.5-year orbit. When Rosetta left Earth, the comet was nowhere nearby. To reach it, the spacecraft needed gravity's help, looping past Earth 3 times, and Mars once over the course of several years, each flyby nudging its speed and path. Then, as it drifted into deeper cold and farther darkness, Rosetta was placed into hibernation to save power. Almost all systems were switched off. Only a small timer, ticking quietly in the dark, remembered to wake it. For about 31 months, Rosetta slept. On a January day in the year 2014, that timer reached its mark. The spacecraft powered on, turned its antenna toward home, and sent a faint signal across space. 45 minutes later, controllers on Earth heard the tiny, delayed heartbeat. A cheer went up in the control room. Rosetta was alive, and its quarry still waited ahead. As the spacecraft approached, the comet changed from a point of light to a lumpy, detailed world, shaped a bit like 2 uneven lobes joined by a narrow neck. Its surface was blacker than charcoal, full of cliffs, pits, and smooth, dusty plains. By late summer, Rosetta slipped into a delicate orbit around this drifting, active body, the first spacecraft ever to do so. The comet's environment was restless. As it neared the Sun, frozen gases within it turned to vapor and rushed out in jets, dragging dust along. These outflows made small, shifting atmospheres and tails, complicating navigation. Still, Rosetta mapped the surface, sniffed the gases, and studied how sunlight reshaped the comet's skin. It watched as pits formed and cliffs eroded, as new patches of ice were exposed and then darkened again. In November of that year, Rosetta attempted something even bolder. It released a small lander named Philae. The plan was simple in theory. Philae would drop slowly to the surface, fire harpoons into the ground, and screw ice screws into place to anchor itself in the comet's weak gravity. But space does not always follow plans. The harpoons failed to fire. When Philae touched down, it bounced once, then again drifting across the comet in long, slow arcs. Finally, it came to rest in a crack, or hollow, tilted and shaded. Its solar panels received only weak light. For about 60 hours, Philae worked as best it could, drilling, tasting, and measuring. It sent precious data about the comet's surface and interior, about complex organic molecules and strange, ancient ice. Then the light faded, its batteries drained, and it fell silent. Rosetta remained in orbit, continuing the mission alone. For roughly 2 more years, it traced paths around the comet, sometimes backing away for safety, sometimes dipping lower for close views. As the comet swung close to the sun, activity surged. Plumes of gas and dust grew stronger, and the landscape shifted. When it moved away again, the jets calmed, and the airless quiet returned. Rosetta itself depended on solar power. As the comet traveled farther from the sun, the energy available to the spacecraft dropped. Keeping it in orbit forever was not realistic. The comet's gravity was too weak and uneven, and uncontrolled drift would eventually risk collisions or escape into an unpredictable path. So, the mission team made a gentle, poetic decision. Rosetta would descend one last time. On the last day of September in the year 2016, the spacecraft began a slow spiral toward the surface. Even as it fell, it kept its instruments awake. Cameras capturing ever finer details of dust, grains, and boulders. Instruments sampling the thin gas, sensors recording the tiniest variations in the environment. Its final images showed the surface in exquisite intimacy. Fractured textures, scattered stones, shadows stretching across subtle slopes. Then the signal ended. The impact was softer than a walking pace. There was no explosion, no bright flash, only a small, quiet contact on a dark, uneven world. Over time, rising dust from the comet's activity may have covered the resting spacecraft. Perhaps it is already buried. Perhaps it lies partly exposed, half in shade, half in light. In either case, Rosetta's body now shares the comet's journey, bound to its icy companion. Long after the last transmission, scientists still sift through its data. The mission changed how we understand comets, how they form, what they are made of, how they evolve as they move in and out of sunlight. Comet 67P continues its looping path, circling the sun, passing within and beyond the orbit of Mars. Somewhere on that uneven surface is a lander tipped into shadow. Somewhere on that uneven comet surface lies a little lander asleep in shadow. And somewhere nearby, slowly decaying in that same faint gravity, is the orbiter that carried it there. Not every traveler in space finds such a quiet resting place. Some burn in our own sky, leaving only a streak of light and a small capsule falling behind. When Hayabusa left Earth in May of the year 2003, it carried a hope that felt almost fragile, that a small spacecraft from Japan could chase down a tiny, fast-moving asteroid, touch it, take a sample, and bring a piece of it home. No one had ever tried such a thing before. Built by JAXA, Hayabusa was light and compact, driven by ion engines, and equipped with a simple sampling device and a tiny lander named Minerva. Its target was a near-Earth asteroid called Itokawa, a stony body around 500 meters long, shaped like a bent potato. The journey was not kind. Damage to its solar panels reduced its power. One of its reaction wheels, needed to keep it steady, failed. Even so, Hayabusa kept going, traveling more than 2 billion kilometers before meeting Itokawa in the middle of the 2005 northern summer. Once there, it became the first spacecraft ever to orbit and try to land on such a small, low-gravity world. Itokawa was not a solid rock, but a loose rubble pile, pebbles, boulders, and empty spaces clumped together by gravity alone. That made everything harder. Minerva was released, but a misjudged separation sent the tiny lander drifting off into space. It never reached the surface. Hayabusa then tried to gather samples by briefly touching down and firing a small projectile into the ground to kick debris into a collector. The first attempt failed. No shot was fired. A second attempt took place amid glitches and partial telemetry. No one on Earth could say for sure whether any grains had actually been captured. Meanwhile, more systems began to fail. Additional reaction wheels stopped. A fuel leak sent the spacecraft tumbling and cut communication for weeks. Many thought the mission was over, but little by little, contact was restored. Engineers nursed the damaged craft back to health, just enough for it to start the long journey home, inching its way with its ion engines, adjusting course in tiny, patient steps. By June of the year 2010, Hayabusa approached Earth for the last time. It released a small sample return capsule aimed at the Woomera test range in Australia. The capsule plunged into the atmosphere behind a brilliant fireball as the main spacecraft burned up above it, breaking apart like a shooting star. Hayabusa itself ended as ash and ionized streaks of light. The capsule, shielded and slowed by parachute, came to rest in the desert. When scientists opened it, they moved carefully, half afraid they would find only emptiness. At first, the inner surfaces looked almost bare, but under microscopes, tiny grains began to appear, dust less than a millimeter across, caught in corners and filters. They were from Itokawa. Against long odds, Hayabusa had done what it set out to do. It became the first mission ever to bring back samples from an asteroid. The story did not end with that one fireball. On the ground, engineers had built spare parts and nearly complete test models of the spacecraft, the way teams often do for a new design. These engineering models, used to test procedures and diagnose problems, rarely leave Earth. In Hayabusa's case, one of those nearly complete spares became the seed of a new mission, Hayabusa 2. Using the hard lessons of the first mission, JAXA's team strengthened and refined almost everything. Hayabusa 2 carried upgraded thrusters, more reliable sampling mechanisms, better navigation, and several deployable landers and small rovers. It launched in the year 2014 toward another near-Earth asteroid, Ryugu. Once again, it used ion engines and gravity assists to wind its way across space. In the year 2018, it arrived. This time, the mission unfolded more smoothly. Hayabusa 2 deployed hopping rovers and a small lander onto Ryugu's rough surface. It collected samples from 2 different locations, including material from beneath the surface, after creating a small artificial crater with a shaped explosive. In the year 2020, it returned a capsule to Earth, again over Australia. Inside were more than 5 grams of grains and fragments from Ryugu, far more than the specks Hayabusa had carried back. Unlike its predecessor, Hayabusa, too, did not end its life in the atmosphere. Its main body passed by Earth and continued on, heading for a new, tiny asteroid that it is expected to visit in the 2030s. Meanwhile, the samples from Ryugu now rest in laboratories, offering clues about the early solar system, organic chemistry, and the origins of water on rocky worlds. So while the original Hayabusa ended as glowing dust in the upper air, its twin, rebuilt from spare hardware and redesigned with experience, still travels. It is rare for a spacecraft's hardware to have a second life, but Hayabusa's test models and backup frames were given a new purpose. The first mission, once criticized for its stumbles, is now remembered as a fragile, hard-won success, and as the ancestor of a more graceful successor. Not every mission returns in triumph. Some fall back toward Earth carrying something precious, only to meet the ground too fast. Genesis, launched by NASA in August of the year 2001, had a simple, delicate goal: catch particles of the solar wind, bring them home, and let scientists study the purest possible samples of our star. To do that, the spacecraft had to leave Earth's atmosphere far behind and wait in a place where the sun's breath could reach it mostly undisturbed. It traveled to the first Lagrange point, often called L1, a region between Earth and the Sun where the pull of their gravity and the outward push of orbital motion balance just enough to let a spacecraft hover in a kind of gentle equilibrium. There, Genesis opened its collector arrays, thin, ultra-clean wafers of materials like silicon, gold, sapphire, and diamond-like films. For more than 2 years, from late 2001 through 2004, these delicate surfaces quietly caught ions from the solar wind drifting in from the Sunday. Each particle was unimaginably small, but over time, the collectors accumulated enough atoms to study. Because the materials were so pure, scientists would later be able to tell which particles were solar and which were contamination. That was the plan. Gather the sun's breath in crystal dishes, then bring it home untouched. When the collecting phase was over, the sample return capsule, holding the fragile arrays, separated from the main spacecraft and headed back toward Earth. The landing sequence was choreographed with care. The capsule would enter the atmosphere, deploy a parachute, and then be caught in midair by a helicopter before it could hit the ground. Similar mid-air captures had been done before. The capsule was not designed to survive a hard impact. The capsule entered the sky exactly when and where it was supposed to, but the parachute never opened. A tiny sensor inside, meant to detect the deceleration of atmospheric entry and trigger the deployment, had been installed backward. To its electronics, the capsule still felt weightless, as if it was in space. The command to open the chute never came. Instead, the capsule fell, accelerating until it slammed into the desert floor in Utah at nearly 200 miles per hour. The impact tore the shell apart, smashed the collector plates, and scattered shards of glass, dust, and soil in a spreading crater. In a moment, the gentle ballet of solar wind collection had turned into something that looked like wreckage. Even so, the mission team did not simply walk away. Recovery crews moved in quickly, setting up temporary clean rooms in the field. They gathered every piece they could find, not just obvious fragments, but powder, chips, and slivers of the collector materials. Later, in labs, scientists developed special techniques to clean the shards and separate out the solar particles from the desert dust. It was painstaking work, but it paid off. Despite the violence of the crash, many of the collected ions could still be studied. From those fragments, Genesis delivered what it had promised in a quieter way: Scientists were able to measure the sun's composition more precisely than before, especially the ratios of different isotopes of elements like oxygen and nitrogen. They discovered that the solar wind has isotope ratios that differ from those on Earth, suggesting that the material that formed the planets had already been altered from the original solar mix. In that sense, Genesis succeeded. It deepened our understanding of how the sun and its planets differ. But the mission also left other traces that cannot be measured by instruments. On Earth, pieces of the capsule and its heat shield likely remain buried beneath layers of sand, tiny bits of metal and glass slowly sinking into the landscape. In space, the main spacecraft bus, its job finished once the capsule separated, was steered into a quiet orbit around the Sunday. Its instruments shut down, its power systems drained. It now circles our star silently on a path similar to Earth's. A dead companion that few people remember is there. Genesis left behind both data and ghosts. A scar in the Utah desert and a mute bus drifting through inner space. Its failure changed procedures for later sample missions. Parachute systems were redesigned. Sensors were checked and rechecked. Quality controls were tightened. Some of those later missions may owe their safe landings to what was learned from Genesis's fall. For the people who built it, the loss was more than technical. The collector arrays had been crafted with great care, materials grown and polished to extraordinary purity, handled with gloved hands in quiet laboratories. To see them shattered and smeared with soil was heartbreaking. Some engineers cried when they saw the wreckage. Others stood in stunned silence. And yet, from within that broken capsule, science still emerged. The ions that could be recovered became more precious precisely because they had survived such violence. Every particle pulled from the shards, every atom identified amid contamination, felt like a small redemption. Every ion, every atom became more valuable because of the accident. Scientists treated every surviving atom from Genesis as something rescued rather than simply delivered. In quiet labs, researchers still lean over those tiny fragments, coaxing secrets from them grain by grain. Somewhere far above, the original Genesis bus continues to circle the sun, drifting through the very solar wind it once helped us understand. It no longer listens, no longer speaks, but it is still there, a small ghost moving through the light that made it. Closer to home, Earth has its own quiet places for retired machines. Thousands of satellites circle our planet. Some are still busy, passing along phone calls, weather pictures, and television signals. Others have already fallen silent. Their fuel is gone, their electronics cold, their work finished. They do not all simply drift wherever fate takes them. Many are guided, gently, to a place set aside for endings, a region sometimes called the graveyard orbit. This graveyard is not a single point, but a thin band of space just above the ring where geostationary satellites live. In geostationary orbit, high above the equator, satellites move at exactly the same rate that Earth rotates. To someone on the ground, they seem to hang in one spot in the sky. This makes them perfect for communication and weather watching. Dishes and antennas can point once and stay fixed, trusting that the satellite will always be there. But the ring can only hold so many steady occupants. Each satellite needs room, so their signals do not interfere and their paths do not cross. As more and more have been launched, the band has grown crowded. The graveyard orbit is the answer to a quietly urgent question. Where do you put a satellite when its time is over, without blocking the view for those still working? When a geostationary satellite nears the end of its life, engineers keep a little fuel in reserve. In its final days, the craft uses that last breath to fire its thrusters and climb a little higher, just a few hundred kilometers above the main belt. Once there, it is gently shut down. Remaining fuel is vented so it cannot explode. Batteries are discharged, moving parts are locked, antennas are turned off. The satellite becomes, in every sense, a husk. If everything works, it will stay out of the way for centuries. If not, if a craft fails early or runs unexpectedly dry, it may never make that last climb, and instead remains among the active satellites as an uncontrolled piece of debris. Those are the ones operators worry about most. Up in the graveyard itself, hundreds of dead satellites now drift. Some served as early communication links between continents. Others watched cloud patterns, monitored storms, or carried military instruments whose true purposes were never publicly described. Now, they are all the same. Silent bodies circling above the equator, slowly twisting, their solar panels no longer tracking the Sunday. There is no air to rust them, no rain to strip their paint, but time still touches them in subtler ways. Tiny micrometeoroids chip their surfaces. Thermal changes make metal expand and contract, loosening joints. The pull of the moon and the uneven shape of Earth's gravity field nudge their paths, making them wobble and drift. Some are still carefully tracked in catalogs and databases. Others, especially older or less documented craft, fade into a kind of statistical background known in principle, but not in detail. Collisions in this high, quiet zone are unlikely, but not impossible. The satellites move slowly relative to one another, which helps. Even so, a single impact could create a cloud of fragments that spreads over time, turning some of the graveyard into a field of shrapnel. This is why end-of-life planning is now considered part of good manners in orbit. When engineers design a new geostationary satellite, they also design its final journey upward. From Earth, none of this is visible. The ring of working satellites and the ring above of abandoned ones are too far away and too faint. But if you could stand somewhere far above the equator and look down with perfect eyes, you might see two thin necklaces of metal, a bright band of active machines, and just above it, a dimmer band of relics, circling forever in a place we made for them. Not every lonely spacecraft ends its story in orbit. Some fall through alien skies and come to rest on worlds far from home, leaving footprints that only instruments have ever seen. On a cold January day in the year 2005, a small probe drifted down through the thick golden clouds of Titan, Saturn's largest moon. Held by parachutes, it sank slowly through air richer and denser than Earth's, listening to the wind, tasting the atmosphere, and snapping pictures through the haze. Beneath it lay a world no one had ever visited. The probe was called Huygens, part of the Cassini-Huygens mission, a shared effort of NASA, the European Space Agency, and the Italian Space Agency. Cassini, the largest spacecraft, had carried Huygens across the outer solar system and released it on a precise course toward Titan. Huygens itself had no engines, only patience, parachutes, and batteries made to last a few hours. As it descended, the orange fog slowly thinned. Huygens began to see the ground below, branching dark channels that looked eerily like river valleys, bright highlands, and smooth lowlands. It measured the composition of the air and found nitrogen as the main gas, much like Earth's sky, but laced with methane. On Titan, where temperatures are far below the freezing point of water, methane and ethane can behave like water does here, forming clouds, rain, rivers, and lakes. In the end, Huygens did not splash into a sea. It came to rest on something solid, a surface that behaved a bit like damp sand. The air around it was unimaginably cold, hundreds of degrees below freezing. The rounded rocks scattered nearby were likely lumps of water ice, as hard as stone in that deep chill, dusted with dark organic particles that had fallen from the atmosphere over ages. For a little more than an hour after landing, Huygens kept working. It sent back images from just above the ground, listened to Titan's whispering winds, and continued to sample the air and surface. Then its batteries, designed for only that short window, ran down. The last signal faded, and Huygens joined the frozen landscape it had just introduced to us. Now the probe sits alone on Titan, the only human-made object ever to rest on that distant moon. No one has seen it since. Cassini made many flybys afterward, but Titan's thick atmosphere and haze make spotting such a small object extremely difficult. We know the general region where it lies, somewhere near the equator, but not the exact rock or hollow. The extreme cold will preserve it. There is no biology to chew its metals, no liquid water to rust it, no strong sunlight to bleach it. Slow winds may drift fine particles across its surface, and methane rain might occasionally fall nearby, carving channels and shifting grains. Over long spans of time, organic haze from the sky may settle over the lander, like dust on an old photograph. Titan itself is one of the most intriguing places in the solar system. A moon with an atmosphere thicker than Earth's, a surface sculpted by non-water liquids, and chemistry that hints at complex organic molecules. Huygens did not search for life, but it proved that Titan is a world with weather, seasons, and change, a place where nature is busy in ways both familiar and utterly strange. Future missions are being planned, including a rotorcraft called Dragonfly that may one day hop across Titan's surface, sampling dunes, ancient riverbeds, and perhaps the edges of methane seas. If it flies, it will deepen the story Huygens began. But Huygens will always be the first, the little probe that fell through golden clouds and left a quiet imprint on an alien shore. In many ways, that first step echoes the early deep space efforts of the European Space Agency, when Europe was just beginning to send its own craft into the wider solar system. For a long time, exploration beyond Earth's orbit was shaped mostly by two players, the United States and the Soviet Union. Their missions carried the first humans, the first lunar landers, and the first probes to other planets. In the 1980s, Europe began to add its own voice, not just with satellites around Earth, but with missions that reached for comets and distant worlds. One of the earliest and boldest of these was Giotto, launched in the mid-1980s. Its target was Halley's Comet, making one of its rare swings through the inner solar system. Giotto was small and sturdy, built like a squat cylinder with a dish antenna facing Earth and a thick shield facing forward. It needed that armor. Flying near a comet means rushing into a storm of dust and ice grains at enormous speed. In early 1986, as Halley's Comet approached the Sun, Giotto swept in to meet it. The spacecraft dived into the cloud of gas and dust streaming from the nucleus, closing the distance to only a few hundred kilometers. Particles slammed into its shield. One impact was strong enough to knock the craft into a brief spin and damage its camera, but Giotto kept transmitting. What it revealed changed how people imagined comets. The bright, graceful tail seen from Earth comes from a core that is dark and rugged, more like a lump of coal than a shining snowball. Jets of gas burst from cracks and pits, carrying dust with them into space. Giotto's instruments confirmed that cometary material is a mixture of ice, rock, and organic compounds, primitive ingredients from the solar system's earliest times. After that first, dramatic encounter, it would have been easy to let Giotto drift quietly away. Instead, mission planners found a way to give it one more task. Years later, in the early 1990s, they guided the aging spacecraft to fly past a second comet, Grigg Skellerup, collecting another set of measurements from a very different icy body. Once that second encounter was over, Giotto's work was done. Its instruments were switched off, its path no longer adjusted. Since then, it has remained in solar orbit. Giotto was not alone in that early European push outward. Another quiet pathfinder was Ulysses, launched in the year 1990 through a partnership with NASA, but steered day to day from Europe. Ulysses was built to study the sun, not by staring straight at its face, but by flying over its poles, a place no spacecraft had ever visited. To reach that strange orbit, it had to take a long detour. It swung past Jupiter and used the giant planet's gravity like a hook, bending its path out of the flat plane where most planets circle. Once settled, Ulysses traced a tall, looping path over the sun's north and south poles, again and again. Its instruments tasted the solar wind, mapped magnetic fields, and counted cosmic rays. It stayed awake for more than 18 years, far longer than anyone had promised, until its power finally faded in the year 2009. Now it, too, is a silent traveler on a tilted track, sliding above and below the thin disk where the familiar worlds move. Other European missions did not chase planets at all, but turned their gaze to the wider sky. The Infrared Space Observatory, launched in the mid-1990s, opened a window on coal dust, newborn stars, and hidden galaxies. Later, Herschel and Planck followed, measuring faint heat from the early universe and the delicate ripples in the afterglow of the Big Bang. These observatories never touched a comet or a moon, but they stretched Europe's reach deep into cosmic history. Closer to home, Smart 1, launched in the early 2000s, tested solar electric propulsion on a journey to the moon. It spiraled outward slowly, sipped power from the sun, orbited our neighbor, and then was deliberately guided into a gentle crash on the lunar surface. It was small and experimental, but it proved that European-built craft could go beyond Earth and linger there, learning. Rosetta, with its comet rendezvous and soft landing, would eventually become one of Europe's most beloved missions. Yet it stood on the shoulders of these earlier flights, simple, focused probes that traded size for daring, working with modest budgets but bold goals. Together, they marked a shift from merely placing instruments in orbit around Earth to tracing paths far into the solar system. Every so often, long after a mission ends, someone will point an antenna toward where an old spacecraft should be, just to listen. In the late 2000s, the European Space Agency briefly tracked Giotto again, confirming that it was still tumbling through space. It did not answer. Its silence simply confirmed what was already known. The craft remained, but its voice was gone. New missions now follow, like the Jupiter Icy Moons Explorer coasting toward the giant planet and its frozen satellites. But the first steps belong to those smaller, early travelers. They earned their place in the quiet fleet that now drifts between worlds. Some missions do not just watch comets, they collide with them. NASA's Deep Impact spacecraft traveled more than 130 million kilometers to reach Comet Tempel 1. It did not arrive alone in spirit. Tucked inside was a heavy copper-filled impactor, essentially a slow, deliberate bullet. The plan was simple and radical. The main craft would watch from a safe distance while the impactor steered straight into the comet at high speed, punching into its surface and throwing out a spray of dust and ice. The impactor was about the size of a small desk and had one job. It would send back increasingly detailed images as it fell toward the nucleus, showing the landscape growing closer in its last minutes, then vanish in a flash of light as it hit. That is exactly what happened. The final pictures revealed a rough, shadowed surface, scarred by ridges, pits, and slopes. Then the feed ended, cut off as the impactor became part of the comet itself. From farther back, the flyby craft watched the plume erupt, a bright cloud glowing in sunlight, filled with fine particles and vapors. Instruments measured the dust grains, the gases, the way light scattered through the debris. The data showed that Temple 1's interior was made of soft, powdery material laced with water ice, carbon dioxide, and complex organic molecules. It was like opening a time capsule from the birth of the solar system. The impact left a crater, but Deep Impact never saw it clearly. The dust cloud was too thick, and the encounter too brief. For a while, no one knew exactly what scar the mission had carved. Years later, in the year 2011, another spacecraft, Stardust Next, flew by Temple 1. Its cameras finally spotted a shallow depression at the impact site, roughly 150 meters across and about 20 meters deep. Soft-edged, almost gentle, it marked the place where human curiosity had literally struck the surface of a comet. Deep Impact's main craft still had fuel and working instruments after its first mission. Rather than let it drift, NASA gave it new tasks: monitoring distant planets for subtle brightness changes and visiting another comet, Hartley 2. That second encounter, in the year 2010, revealed a tiny, hyperactive comet shaped like a peanut, with jets blasting out carbon dioxide and carrying icy particles away like exhaust from a miniature engine. Eventually, the spacecraft began to fail. In the year 2013, contact was lost. Investigations later suggested that a timing error in its onboard computer caused it to lose awareness of its orientation. Unable to point its antenna toward Earth or its panels toward the sun, it likely ran out of power and went dark. Now the flyby craft orbits the sun on a stable path, circling roughly every 1.5 years, another dark object moving among many. The cloud of debris from its impact on Temple 1 has long since spread and settled, some back onto the comet, some carried away into space by later jets. Most missions leave no mark but a trail of data. Deep Impact left both measurements and a small crater, a physical imprint on a drifting fragment of ancient ice. Not all failed dreams end with a controlled impact on a comet. Some end much closer to home, within the thin shell of space around Earth. Late in the year 2011, a Russian rocket rose from Baikonur Cosmodrome, carrying a spacecraft called Phobos Grunt. Its name combined the Martian moon Phobos with a Russian word for soil, describing its goal: land on that tiny moon, scoop up samples, and bring some of its surface back to Earth. It would have been Russia's first interplanetary sample return, a bold echo of Soviet-era exploration. The launch itself went as planned. Phobos Grunt reached low Earth orbit and prepared for the next step, a burn of its upper stage to send it toward Mars. That burn never came. The propulsion module stayed silent. Instead of leaving for the Red Planet, the spacecraft remained circling Earth. Controllers tried for days and then weeks to wake the dormant stage or change the trajectory. Signals were sent, commands crafted, ground stations enlisted. Nothing worked. Phobos Grunt had power. Its solar panels unfolded, and its systems were not entirely dead. But without that critical engine ignition, it was stuck, bound to Earth by its own unfinished journey. The loss hurt more than just one program. On board was China's first Mars-bound spacecraft, Yinghuo 1, meant to separate at Mars and orbit the planet on its own. There were biological experiments designed to test how tiny life forms might endure the long journey. All of these hopes remained trapped within Earth's gravity, never reaching their intended world. This was not Russia's first attempt to touch Phobos. In the late 1980s, the Soviet Union launched Phobos 1 and Phobos 2. One died en route due to a mistake in command. The other reached Mars, returned images and data, and then fell silent, just as it prepared to send landers to the moon's surface. Phobos Grunt had been designed with those failures in mind, an effort to finally complete what earlier missions had started. Instead, it joined them as another unfulfilled story. For about 2 months, Phobos Grunt circled Earth, its orbit slowly decaying as the thin outer atmosphere brushed against it. On a January day in the year 2012, it fell back. Most of the spacecraft burned up high above the Pacific Ocean. Any surviving pieces would have splashed into remote waters, far from human eyes. The mission's end left more than debris behind. It deepened questions within Russia about funding, oversight, and the readiness of its hardware for complex deep space tasks. There were discussions of a follow-up mission, sometimes called Phobos Grunt 2, possibly in partnership with Europe, but those plans never solidified. Resources shifted back toward nearer-Earth projects and long-term collaboration on the International Space Station. What remains now are design documents, test units stored in labs, remembered lessons about rushed schedules and fragile electronics, and the lingering sense of a chance that nearly was. Somewhere in old data logs is the record of those brief orbits and the faint signals received. Somewhere in the minds of the engineers is the shape of the spacecraft they built, watched rise into the night, and never saw reach its destination. In the widest story of Mars exploration, Phobos Grunt is one of many attempts that fell short. Yet around the planet today, and on its surface, are other machines that manage to hold their course and find their paths. Among them is one from another nation entirely, a quiet witness that slipped into orbit on a modest budget and stayed for years. ISRO's Mars Orbiter mission, still whispering from afar. In the cool air above the Satish Dhawan Space Center, in November of the year 2013, a slender rocket rose carrying India's first interplanetary traveler. Its name was simple: the Mars Orbiter mission, often called MOM, for the Indian Space Research Organization, ISRO. This was a first step into deep space, into a realm long shaped by NASA, Roscosmos, and the European Space Agency. MOM was built on a budget small enough to be compared with a Hollywood film, roughly $74 million for the entire adventure: launch, cruise, orbit, and science. Designed and assembled in less than 2 years, it became a symbol of careful engineering and frugal ambition. Some people admired the efficiency, others doubted it could work. The spacecraft, light and compact, rode into Earth orbit on a PSLV-XL rocket, the most powerful version of India's workhorse launcher. Because that rocket could not throw it directly to Mars, MOM had to spiral outward in a series of measured steps. Using its own main engine, the spacecraft performed a chain of apogee-raising burns, stretching its orbit around Earth wider and wider. Each loop took it a little farther until one final push let it slip free of Earth's gravity and begin a journey of about 300 days toward the Red Planet. In September of the year 2014, MOM arrived. One critical maneuver was still ahead: Mars orbit insertion. In the control room, engineers watched screens, quietly, waiting. If the engine refused to light, if the timing was wrong by even a little, the spacecraft would miss Mars and drift forever around the Sunday. Instead, the burn unfolded as planned. The engine fired, the spacecraft slowed, and Mars gravity caught it. India had reached another planet on its first try. On board, 5 instruments waited. A color camera watched the surface and thin atmosphere. A methane sensor searched for the faintest hints of gas that might point to geological activity or something more mysterious. Other instruments studied the upper atmosphere, dust, and surface features from afar. Compared with large missions like NASA's MAVEN or the European Mars Express, MOM's payload was modest, but that was not really the point. Its true purpose was to prove that India could design, launch, and operate a planetary mission of its own. The orbiter was officially expected to last about 6 months. It stayed for years. MOM sent back images of Mars as a whole crescent hanging in blackness, wisps of cloud trailing over ancient craters, the pale cap of frozen poles shining at the edge of the planet's curve. Its camera did not have the sharpest eyes, but it offered a gentle, wide view that people at home could feel connected to. Engineers nudged its orbit from time to time to make the most of its fuel and keep its solar panels in good light. Season after season, it continued to work, quietly monitoring conditions high above Mars. By the time the year 2020 arrived, the mission had already lived far beyond its promised span. In the year 2022, the silence came. ISRO later explained that MOM had likely exhausted its fuel. Without the ability to keep its body properly oriented, the spacecraft would have struggled to point its solar panels at the Sun and its antenna at Earth. Attempts to re-establish contact failed. There were no last photographs, no farewell message, just the absence of a familiar whisper. Even so, MOM is almost certainly still there, looping around Mars on a path it can no longer adjust. It has become one of the many dormant machines circling the planet, a quiet companion to the still living orbiters and the ones that have already gone dark. Its presence is unique. The first Martian observer from a country that had never before sent a spacecraft so far. On Earth, its influence lingers. The mission trained a new generation of engineers and scientists. It captured public imagination, strengthened support for space science, and gave ISRO the confidence to attempt more lunar missions like Chandrayaan-2 studies of Venus, and talk of future Mars projects. MOM did not try to outshine larger missions. Instead, it demonstrated that with careful planning and clear goals, even a newcomer could cross the gulf between worlds. It helped shift the story of exploration from a tale of a few powers to a chorus of many voices. Far smaller travelers are now adding their own quiet notes to that chorus. When the first CubeSat was sketched out in university labs in the early 2000s, it was little more than a teaching tool. A cube, 10 centimeters on each side, roughly a kilogram in mass, simple, inexpensive, and meant to hitch rides into orbit alongside larger spacecraft. Students and small teams used them to test sensors, radios, and tiny computers. No one knew that, in time, some of these little boxes would slip beyond Earth's neighborhood altogether. CubeSats are built from standard units. One unit, called 1U, is a single small cube. Larger versions, 3U, 6U, 12U, Stack these units together into longer shapes, adding room for batteries, antennas, and sometimes miniature propulsion. They lack the thick insulation and multiple backup systems of traditional deep space probes. A glitch that a larger spacecraft might shrug off can be fatal to a CubeSat, but they are quick to build, relatively cheap, and open doors for groups that might never afford a full-scale mission. One of the first CubeSat adventures to truly push the limits was Mars CO, short for Mars Cube 1. In the year 2018, two identical 6U CubeSats, nicknamed EVE and WALLE, launched alongside NASA's InSight lander. Their task was simple, but critical. Fly behind InSight, listen as it descended, and relay the lander's signals back to Earth in real time. It was a test to see whether small satellites could survive the journey to Mars and be useful along the way. They did. As InSight plunged through the thin Martian atmosphere, the twin CubeSats listened and repeated its heartbeat homeward, letting controllers follow the landing minute by minute. Along their path, they also took images, proving that tiny platforms could carry cameras and radios all the way to another planet. After they flew past Mars, though, they had nowhere else to go. With no large propulsion systems and only limited power, their signals slowly faded. First one went quiet, then the other. The twins slipped into silent orbits around the Sun, becoming two of the smallest interplanetary ghosts. More CubeSats followed. When NASA's Artemis 1 mission launched toward the Moon in the year 2022, it carried 10 CubeSats with a wide range of goals: scouting for ice in shadowed lunar craters, mapping hydrogen near the South Pole, testing navigation technologies, even attempting a tiny lunar landing with a Japanese craft named OMOTENASHI. The ambition was high, the risks, too. Some of these little explorers never fully woke up after deployment. OMOTENASHI suffered communication problems and missed its chance to fire engines for a landing. Another CubeSat, Lunar HMAP, lost its propulsion system and could not enter the planned lunar orbit. Without course corrections, their paths bent away from the Moon into wider loops around the Sunday. Small, fragile, and now uncontacted, they drift as invisible specks in the inner solar system. Their failures are not meaningless. Each one teaches designers something. How electronics age in deep space, how much propellant is really needed, how to protect tiny radios from interference. Newer CubeSats are already carrying better thrusters, more robust software, and smarter power systems, because earlier ones did not survive. The field is young, and much of its early work is written in silence. These tiny craft rarely earn headlines. They seldom carry high-definition cameras or charming names that the public remembers. Yet, they mark an important shift. Exploration is no longer the sole province of large agencies and flagship missions. Universities, small companies, and new spacefaring nations can send their own boxes of instruments into the dark, try bold experiments, and sometimes fail in ways that barely register outside a few small rooms. But all those attempts slowly widen the path for others. Some CubeSats will circle Earth until air drag pulls them down to burn in the atmosphere. Others, especially those sent toward the Moon or beyond, will remain in space for a very long time, tracing quiet arcs around the Sunday. They are the tiniest ghosts in the story of exploration, easy to overlook, hard to find again, but each one a marker of how far human curiosity now reaches. Long before CubeSats, another kind of listening post was sent into a different kind of quiet. In the early 1970s, NASA launched a spacecraft toward the moon that was not meant to take pictures at all. It was called Explorer 49, part of a series of radio astronomy missions. Instead of eyes, it carried long, delicate ears. Its purpose was to listen to the universe at very low radio frequencies, sounds that cannot be heard from Earth because our own planet is too loud. Earth's atmosphere and the web of human radio transmissions fills space around us with noise. Even on the night side, where the ground is dark, the air crackles with signals from broadcasters, radars, and communication networks. To find true radio silence, scientists look to the far side of the moon, where the bulk of that rocky sphere could block Earth's interference like a shield. Explorer 49 was launched in June of the year 1973 and guided into a wide, looping orbit around the moon. Once there, it slowly unfolded 3 extremely long wire antennas, each one stretching roughly 230 meters. With those spidery booms extended, the spacecraft became, for a time, the largest radio telescope ever flown in space. Its shape was uneven, its motion not perfectly graceful, but its reach into low frequencies was unmatched. As it swung behind the moon, into the region where Earth's radio noise was blocked, Explorer 49 listened. It recorded low-frequency signals from our galaxy and beyond, murmurs from pulsars, emissions from distant galaxies, the broad glow of cosmic background radiation. These waves do not draw sharp pictures the way visible light does. They create fuzzy maps and smeared patterns, but even those soft images carry information. They tell of magnetic fields stretched across vast distances, of energetic particles moving through interstellar space, of structures shaped long ago. For about 2 years, the spacecraft circled and listened, building a survey of the low-frequency sky that could not be made from the ground. Eventually, its systems aged, its transmissions faltered, and contact ended around the mid-1970s. Orbital models suggest that its path slowly decayed, and that, at some point afterward, it likely fell and struck the lunar surface. No one saw the impact. The antennas that once caught whispers from the cosmos may now lie twisted and buried in dust. Explorer 49 occupies a small, almost forgotten corner of space history, but its role was quietly important. It showed that the far side of the moon can serve as a natural radio observatory, shielded from Earth's constant electronic chatter. With limited instruments and modest technology, it reached into frequencies never before mapped in space. Today, when scientists dream about a radio observatory on the far side of the moon, they still whisper the name Explorer 49. It is a reminder that not all great discoveries arrive with flags and footprints. Its long antennas, stretched like ghostly threads, listened quietly to signals that began in distant galaxies and drifted across billions of years. In an age of moon boots and Mars landers, Explorer 49 simply turned its back on nearby worlds and listened to the wider cosmos. Another small machine, launched even earlier, did almost the opposite. It looked very close. Mariner 4 was the first spacecraft to show us Mars as it truly is, launched by NASA in late November of the year 1964. It was little more than a metal frame, solar panels, and a modest camera, lighter than many of today's family cars. Its task sounded simple: fly past Mars once, measure what it could, and take a handful of pictures. The journey took more than 7 months, a long, slow arc through cold space. On the 14th of July, 1965, Mariner 4 swept past Mars at its closest point. Its camera, simple by modern standards, captured just 21 images in black and white, line by line. onto a tiny tape recorder. Those lines later trickled back to Earth over weeks, a drizzle of numbers that engineers patiently turned into pictures. When the first image was reconstructed, it was not the world many had hoped for. Mars looked old and harsh, cratered plains, no seas, no obvious rivers, no gleaming cities or signs of canals. The atmosphere, as Mariner's instruments revealed, was whisper-thin, mostly carbon dioxide, at less than 1% of Earth's surface pressure. The spacecraft detected no strong magnetic field, no comforting shield like the one that wraps our own planet. For dreamers raised on stories of Martians, it was a quiet disappointment. For scientists, it was a revelation. At last, Mars was not an idea, but a place, seen up close. After the flyby, Mariner 4 had no way to turn back. It slipped into an orbit around the Sun, looping inward and outward, crossing the paths of Earth and Mars, but never coming close enough to trouble either. For a few more years, it continued to send back measurements of cosmic rays and solar wind, using what little power and memory it had. Eventually, its tape recorder failed, its systems faded, and contact was lost in the late 1960s. Now it circles the Sun silently, every 20 months or so, a tiny relic, tracing the same path, again and again. It is easy to forget how fragile and simple its heart was. The commands that told Mariner 4 when to turn and when to take a picture were written for a computer that would seem almost toy-like now. When the data began to arrive, slower than expected, some engineers grew impatient. They took raw numbers as they came, wrote them out on paper, and assigned colors to different brightness levels. With colored pencils, they shaded a grid by hand. Before the official photographs were even processed, that rough, blocky sketch became the first human-made picture of another planet's surface. Behind Mariner 4's success, and behind many of the ghostly probes still wandering today, are computers that feel like ancestors of old home machines. TRS-80, Apple II, and others from those early years. The computers that flew on Voyagers, Pioneers, and their cousins were not powerful in any modern sense. They ran at slow speeds, used word lengths of just 18 bits, and stored their programs in tiny amounts of memory, measured in tens of kilobytes. Some used magnetic core memory, where information lived in the direction of magnetized rings of metal instead of in silicon chips. What they lacked in speed, they made up in dependability. Their programs were written in lean assembly language, line by line, by people who had to think about every bit they placed. There were no operating systems as we know them, no complex layers of software. Everything that ran on those machines was designed for one mission, tested over and over, and then sealed in place before launch. The goal was not cleverness, it was survival. Voyager 1 and Voyager 2 still carry those old computers. Engineers on the ground have spent decades nursing them along, rewriting code to bypass failing memory, turning off non-essential systems to save power, and carefully scheduling every task. The machines on board would struggle to display a single modern web page, yet they have guided spacecraft past all the giant planets and now into interstellar space. Pioneer 10, with a computer that could store just a handful of commands at once, stayed alive for more than 30 years before its voice faded. Slow and steady, they outlived their makers. As technology advanced, probes like Galileo, Cassini, and the Mars rovers adopted more capable processors, often radiation-hardened versions of chips already considered old on Earth. Even now, designers tend to choose proven hardware over the newest thing. In space, the latest and flashiest is far less important than the calm, predictable, and tested. These quiet computers, closer to vintage home machines than to modern phones, became our minds in the dark. But while their thoughts may be gentle, their bodies do not simply disappear when their work is done. Every satellite, every probe, every spent rocket stage obeys the same rule of motion. Once launched, it keeps going until something slows it or pulls it down. In low Earth orbit, a hint of atmosphere eventually drags objects back, turning them to streaks of fire in the sky. Higher up, especially around geostationary orbit and beyond, there is no such easy ending. Many old machines become ghosts, circling indefinitely. Sometimes those ghosts collide. In the year 2009, an active Iridium communications satellite struck a defunct Russian satellite named Cosmos 2251. They met at a relative speed of tens of thousands of kilometers per hour. Both were shattered, creating thousands of trackable fragments and many more too small to see. Each shard, even if no bigger than a fist, became a potential hazard for other spacecraft. The risk that had once seemed abstract suddenly felt very real. Today, networks of radars and telescopes watch the sky for such debris. The United States Space Surveillance Network tracks tens of thousands of objects. Other nations and private companies add their own eyes. When a piece of junk or a dead satellite is predicted to pass too close to something important, operators can perform a small avoidance maneuver, nudging a space station or weather satellite just enough to let danger slip by. Each of those moves costs fuel and planning, a tiny tax paid to the past. Farther away, where probes travel between planets or slip out of the solar system, tracking becomes more delicate. The machines that listen there make up what is called the Deep Space Network. 3 families of huge radio dishes placed in California, near Madrid, and near Canberra. Together, they watch the sky so that at almost any time, at least one can see a given spacecraft above Earth's horizon. They catch whispers from Saturn, from Jupiter's moons, from solar probes close to the Sun, and from the distant voyages at the edge of the heliosphere. The Deep Space Network is built for missions that are still alive. Each antenna has a schedule, carefully shared among many spacecraft. A few hours might go to a Mars rover, a few to a Jupiter mission, a few to a probe diving through the Sun's corona. Old, silent craft have no place on the calendar. Once a mission is declared over and a spacecraft stops answering, the dishes move on. The hardware in space may still be there, but the ears on Earth look elsewhere. For a while, we remember. The last known position and trajectory of a probe are written down. Orbital models can predict where it should be, months or years later. But small forces, tiny leaks of gas, minute pushes from sunlight can change its path. Eventually, the uncertainty grows so large that somewhere along this line becomes the best we can say. A few craft, like the image satellite that briefly woke up again after more than a decade of silence, surprise us. Most do not. In public catalogs, old probes are often just lines of text. Name, launch date, status, no longer in contact. Some are still tracked as physical objects, especially if they remain near Earth. Others, far away in heliocentric or escaping orbits, slip out of the lists and into a more abstract existence, known only to history and to the quiet mathematics of celestial mechanics. They are still moving, but no one listens for them now. So we are left with a strange kind of cemetery, one without markers or fences. Some tombstones circle high above the equator in graveyard orbits. Others drift about Mars or lie on the moon. or rest on comet surfaces and asteroid slopes. Some speed outward on paths that will never return, carrying golden records, plaques, and frozen code. Their usefulness is finished. Their data already changed our maps and theories. Yet their bodies remain, small artifacts of a young spacefaring civilization, scattered through the dark. From a distance, if you could see them all at once, they might look like faint embers, cooling slowly as their power runs out, and their metal frames fall to the temperature of deep space. Each one is a memory you can touch, of the hands that built it, the eyes that watched its launch, the hearts that waited for its first signal. Even when the networks stop listening, those traces endure, moving on in silence. Somewhere beyond Mars, an old probe still circles the Sunday. Somewhere behind the moon, a broken antenna may lie half buried in dust. Somewhere above Titan, a small metal shell sits alone in the cold. We no longer hear their voices, but the paths they follow and the lessons they left behind are woven into every new mission that rises on a column of fire. And in that way, the forgotten satellites are not truly gone. They are the quiet company that travels with us, ghost lights marking how far we have already come.